usual mistake. So hi everybody. So thank you for joining this presentation today. So as has been mentioned, my name is Freddy Locu. I'm based in Montreal, in Canada, and I'm leading the AI machine learning team of Thales in North America. I'm also an external collaborator at NRIA, and I'm going to present some work on explainable AI. So that's a term that you may have heard before. And the goal of this session, so it's a 90-minute session, is trying to demystify this, try to give you some ideas of why we do address this challenge, what might be the solutions, and just go deep in the code. So towards the end of the presentation, we will have a hands-on session. So you'll have the links for the different source code, and the only requirement that is needed, it's that you need to have a Google account, because we will use the Google Colab setup for running codes, which offer free GPUs, and that make your life much easier, because you can easily replicate the code, but just accessing, replicate on your drive, and then run and it should just run as a charm. Okay, so let's get started. So a bit of outline. So it's a 90-minute session. Um, so so I'll spend the first 10 minutes giving you introduction, motivation, and evaluation. So just try to give you insight of why that's an important topic, and why we should care, and what are the recent advancements in the area of machine learning. So that will be the second part. And the third part will show you some example of application. So depending on which industry you are, there's probably a need for you stakeholders or for your developers to understand, when they build a machine learning system that make decisions by training a model out of large amount of data, then how you can debug it, on how you can explain, on how you can easily compare models, and there are a few applications that I will describe later. And then the very last part, it will be on tools which are available. And again, the XAI is a term which has been coined and have been studied for years. So the number of publications and tool set is quite huge. So at the end of the presentation, I gave a list of number of open source projects or commercial projects that you might be interested in digging in. So that's for your information. We only focus on the 4 or 5 open source code that you will have access to, that you can run on the GPU offered by Google. Okay, so just in terms of scope, so in explainable AI, there's many interpretation. It's a research topic still, so you'd see a lot of publication in the domain. It's getting much more embraced now by the industry, and the reason why is because of the critical dimension of the AI when putting to a system in hands of human or machines. That you need to control what's going in there. And what I want to mention before we get started, it's not an exhaustive survey. 90 minutes is very short. Even if we give a link to a 4 hours tutorial on the topic, it's very broad, it's very large. And when we say explainable AI, usually people mean explainable machine learning. So keep in mind that here we will be mainly focusing on the machine learning dimension. It's a multidisciplinary, so it's not only AI, it's touching the user, it's touching social dimensions, so it's touching bias. And then when we discuss bias in model and data and algorithm, then it go much beyond the computer science field. So it's go to HCI and social sciences. There are many domain-specific work which are hard to uncover. So again, you may have seen some of those existing work in the past, and are not probably mentioned in this survey here. And there's many papers that do explanation, but they don't mention explainability and interpretability. And that's also something to be careful with. People might confuse or might use the same word for saying I do interpretation, explanation, but it's not the same thing depending on who you're talking with and what your stakeholder means. One interpretation and explanations are different, and so they need proper different definitions. In terms of AI adoption, that's a broader slide here that just position where explainable AI is. It's really what has been really putting a lot of attention now. It's because if you want to push models derived from large amount of data, and you deploy in with critical systems, they need somehow to be trustable. So the human need to trust what the model is particularly computing or predicting or trying to infer, and explanation is crucial. And in the same way, responsibility and validity and dimension on robustness and privacy is also very important. So as soon as we're touching and building a model which is derived from large amount of data and try to detect particular patterns, then you need to be accountable for, or the company needs to be accountable in many different dimensions. And one way to try to go towards that direction is in the explainable AI dimensions. And that's where we will focusing in today. We won't focus on, of course, if you want to have a model running and deploy at large scale on critical systems, of course, you need to make sure they're robust to attacks or to perturbations or to change in distribution shift in data distribution. Of course, you do need that, but here we're only focusing on the explanation part. So in terms of motivation, you may have seen GDPR a few years ago that mentioned that it's a must that now that when we put systems and decisions, which is done on a European citizen, that you need to provide rational and explanation. And then you also have the same dimension in California. You have similar, well, not exactly the same, but similar kind of constraints and rules that dictate that you need to provide some model understanding for validation purposes. So a bit more of an of business perspective. So the way I like to zoom on the topic is think about where is AI really had an impact right now, and where we do want it to have an impact. So now, well, obviously AI is filled by large amount of data, and the data is, well, has been mainly well captured and structured by social media related industries, or by really customers, customer centric and technology companies. So if you think about Netflix and Facebook and Amazon, they do collect data, and they do have way of capturing and structuring information, and then they have access to all of this information, and then they can make decision recommendations and make sure that you have the right recommendations and they push the right ads in, and that's one of the big source of revenue of those companies. But if you think about when the system goes wrong, it's when you have the wrong recommendation. But at the end of the day, it's not really a big deal. And the same if you do tagging of a picture of a person on a picture of your friends, if they don't tag the right person, it's not really the end of the world, right? So they make a mistake, they can change, they can adapt, but it doesn't really have a huge impact. In the worst case scenario for a movie, you spend a bad 90 minutes, but that's mainly it, right? But if you think about critical systems, so there are systems where you build a model for detecting, here in this case, underwater mines, and you put it in. It need to be embedded in the systems, and then you push it with many experts, and what they are doing is capturing those mines and detecting, and if that's a mine that they need to remove from the water, then they have recommendation for doing it, and they keep it. And it's take a large amount of time because it's very sensitive. You need to be careful about the position of the mines. If it's a mine, at the end of the day, if it's not, or if it is, and you miss it, it may have huge impact on people, or on our generation later on. So that's what critical system is, and deploying a model that makes the wrong decision and not being able to debugging it or to have an understanding, it's very problematic. The same if you start deploying such systems in cars or in trains here. Well, same challenge. You put a model that tries to make self-driving trains, and if they make the wrong decision because of whatever reason, well, you need to get some kind of a human in the loop and need to capture the rationale of what the system might be doing a particular decision at a particular time, and that's very important. And that's very important for certifications, because when you push those software, those systems in those critical infrastructure, it may have a huge impact on people, on our safety. But it goes much more critical systems. You may have seen the compass recidivism bias that the system has. So it was a few years back where the jurisdiction in the US tried to figure out which particular person might be subject to recidivism on an offense, and they analyze data, and what they aim at, what they captured is that the algorithm which was built on biased data, and because the collection of the data was also biased, they end up in having an algorithm which was at the end biased towards particular population, and that was quite tricky, and that's what some of states were using. So and again, only using the systems and not trying to challenge it, and not trying to understand what is going on, it's very problematic. So, and you need to have systems that provide explanation well, offline, so you can debug the system and make it better or make it fairer to some extent, or you can use it afterwards just to see what happened and what why the system is not doing the right decision. And you have many of those examples. I won't list all of them, but many examples where systems are being subject to bias, or they were not able to expose explanation, and they were still deployed, and they have huge impact on people. And if you think about systems that have this what we call the learning loop, so they keep learning. So if the data is biased for a particular subset of a population, and you keep replicating and build a model towards the existing population that you have, while obviously you will still well, harm the subpopulation which is underprivileged, so and so on and so forth. So the system will get more and more discriminating, and that's the goal of a machine learning model, is to find the right discrimination, so it can find this job better by doing classifications and finding which features we might need to use for strongly finding the discriminations and finding a right way for doing the classification. And then that's the goal of the system. And the goal of explainable AI is to figure out where these things happen and when it's not fair, or when it's not right, or where it does have an impact on particular population. And here you have the case of FICO, which is an institution that gives you a credit score. And they started a challenge back in 2018 in the RIFS, where they asked researchers to figure out what might be an explanation for a machine learning model that to credit authorization or credit scoring for loan approval. And they wanted to have some explanation, because at the end of the day, I mean, those banks or those institutions are regulated and need to provide reason why they expose a particular decision, and they need on paper, they need the explanation. And yeah, you have other examples in healthcare and medicine. So here I list a few papers that you might be interested in that. So read those and even more. So, well, the other example of bias. So okay, so an explanation. So explanation in a nutshell. So what really is the explanation? So basically, you can see machine learning model, unless and again, machine learning models is not always a black box, but let's say it's a black box, and it's complex enough that it's difficult for you to to go and check exactly what among. There's so many features and there's well, information is not so transparent. So the user is getting an information back, and he might not get it first because it's based on his experience or her experience. She would thought that it should be something different. So then you have a challenge about the different stakeholders, the business owner, the customer support, which might say, okay, well, can I trust this AI decision? How do I answer this customer complaint? How do I monitor and debug this model? And it's basically stakeholders at the end of the day that say, you give me something, you give me a tool that give a prediction, that's good. But then I need to challenge it to make a final decision. And if I want to challenge it, I need to interact with the system. But the way it's done, it's in the majority of cases, it's designed as black box. And again, it could be much more transparent, but when it's designed as black box, it's difficult to query it and to get your answer back. So you won't get explanation in a very first shot. And it's an explainable explanation should be really at the core of the core design of AI products. So it will be really when you do train, when you do quality assessment, when you do deploy, when you do predict, when you do A/B testing, every time at every step you should check if the model is doing the right thing. If at training there's something wrong, there's a bias detected, or some of your tools, some of the explanation provides some kind of weird behavior or some kind of bug or a classification which is always wrong, or a population which is always has an accuracy lower than others. I mean, those tools should be used for debugging your system, because you're doing a training. After training, you have the model, but after you have the model, if you do deploy in production, usually the data that will fit in the model might change, and the behavior of your customer might change. So the model that you might be using might not be relevant in 2 days, 5 days, a week, a month later on, depending on what, and because people are changing habits and they're changing their behavior, and you need to keep track of this evolution. And again, if it's not after only training, it's only also after evaluation and after testing. So after you deploy it and you get the prediction, you want also to get explanation on why the model is deviating from a particular set of good accuracy scores. And the same for A/B testing. You want to know why this solution is better than the others. And when you do the monitor and you do debug, it's the same thing. So it's very crucial that you have all of these mindset. When you deploy from the very beginning to the end, you keep explanation from each and every step. That's really crucial. Okay. Yeah. So an example, and here it's one screen of, I mean, based on what I've seen and what I've discussed with experts in terms of explanation, you will see more and more of those techniques later in later slides. But I wanted to show you what might be something that you might see as explanation. All of what I was going to describe now, it might not be relevant depending on the industry or the use case or the application. But it's something you can pick and choose and say, okay, this is what I want to do. What is what I want from an explanation purpose? So here is an example where it's an end-to-end when the human is interacting. You don't only want the explanations to make your model better and make it systematic, and that's one way. In machine learning, this is what we want to do. We want to have our model getting better, so you get explanation, and systematically you can make it better. But sometimes it's for the human to make the right decision. And for making the right decision, the human should be able to ask the question at a given time, and might be able to rephrase it, and may be able to pinpoint on particular domains or areas. So for instance, here, very simple case, you have a fish, you want to predict what is it, so it's a classification task. And you get a result. The second question is, why do you get such particular results? And that's the human who's asking, and the system I get back and say, oh, well, this is the way I've been discriminating and comparing these pictures with others. And the third say, all right, but I think actually you bias towards the background. So and then the third question might be, which training example did you use and what was the most influential ones? Because in explanation you can get the one which are closest to your particular representation and which have been used in the training model to figure out which class you might be part of. And then the fourth question might be, oh, but what if I change the background? Because I initially thought that the background here might be biased towards detecting this. And if I would have only changed this picture or keep the background, I would have taken the same result. And then the system, and then you challenging the system, say, what if we remove this? What if it was that color? What if we just rotate it? What if I make it bigger? What if, and then you can see, you get your understanding and say, okay, that model sounds like it's robust. It's answering the questions properly, and I get my particular information on what we should be doing. And one thing I wanted to highlight is on the evaluation. So I think it's very important because explanation could be used in many different ways and evaluated in many different ways. And depending on what you want to do, again, if it's only for a system to make it better, maybe you care about the accuracy of the explanations, and maybe you care about how succinct is it. So then I can reuse those two elements and basically re-inject in my model as new features. So the next time is even better and better. And sometimes it's for the human, so then you need much more comprehensibility. So something that the human can easily consume. Sometimes you want to make sure that you pick and take every corner cases, and you pick every questions. Potentially you have an answer for it, so it's much more on the completeness. And sometimes you do care about the explanation, but what you want to do is that the explanation that you get back is actionable somehow. So if they give you information that what can one action? So what can we do with these explanations? If you tell me this is this class because the background is whatever, then you say maybe I don't want to be dependent of the background, so maybe I need to shift and augment my data, so then every time the background is seen, I don't get this explanation anymore because it's not really relevant. So that will help you to basically bypass some explanation, and that's something which is actionable, and actually actionable in terms of making your model better. So that's something which is very important to be considered. So let's go a bit deeper now on the different techniques. So I hope I give you the right level of motivations and how we could see explanation and why evaluation is important. But let's spend some time on the different domain of explanation. So I have a few slides that describe. Here you see AI and the different subtopics. So usually, if you attend conferences like ISHCAI or AAAI, which are major conferences in the broad topics of AI, so very broad. So it's not only neural network; it's touching scheduling, planning, search, game theory, knowledge representation, logics, and robotics. So it's very broad, and all of those domains, they have their sub expertise, and the way and interestingly, explanation of the system that they are building, because they are supposed to be, or they aim at being intelligent systems, they all ask the questions, why do I get this particular answer? If it's for predicting a model, or if it is for minimizing a constraints in a multi-optimization task, or if it is for a planning objective, so you want a robot to do something or to go a particular location, when it takes a particular path or a particular structure, or it takes particular actions to turn left, to pick an object, or to organize things, there is reason why. So and people and experts, they wanted to explore this particular topic. So here I want you to give you an insight that when you say explainable AI, it's not only machine learning, it's not only the model that we want to explain, build on large amount of data, it's also the fields, and that's also very important for you to be considered. So in AI broadly, we ask the question how to summarize the reason, and the reasons might be motivations, the justification, understanding for AI system behavior and explain the cause of their decision. So if you look at machine learning only, you have many tools which have been available for years and which help understanding correlation across different features. You have dependency plots, feature importance, surrogate models. There have been tools which have been available and which are very useful and brilliant for debugging the model, and that's really important to use. If you look much more on the computer vision dimensions, we dig much more at the features, visualization features, and you have many ways. So they're basically gradient based. So when you do train a deep neural network, when you do the back propagations, you try to identify which of the neurons have been activated, and you back propagate this all up to the pixel level. So you see which pixels are the most importantly on the for these particular explanations, and that's called saliency maps. And here you see a list of different approaches. So you have smooth gradient, GradCam, and many others, and they basically will show you on a picture which pixel might be the most important. You do have also explanation in multi-agent systems. So multi-agent systems, they are agents, they have their own actions and objectives they want to do, and basically they organize as a community or as an environment, and as a community they aim at reaching an objective of, I don't know, of being healthy or being wealthy or whatever might be the objective. And each agent has their own individual objectives, and you try to figure well, what might be how they did organize as a community to end up reaching the objectives, and you try to see why you end up having individual purpose, maybe just not prioritize anymore because they're aiming at benefit the community level, and that's the agent-based perspective. You do also have in planning, as I mentioned, so you try to reach an action, and the question is then how you reach these actions and how you reach this particular goal, and what are the set of actions that you need to be using. In constraints and satisfaction and search, you have an optimization task. So you have many constraints. So you want to go for holidays, and you have constraints about geography and budget and many others. And the explanation is which constraints have been satisfied, and then which one might need to be relaxed. So sometimes it's an optimization task that you can resolve, and being able to figure out that this particular content is so hard that you won't be able to find the solution for it. Game theory, it's another field where it has been used. In robotics, it's a field where they combine well, computer vision and planning and object detections. So think about this as a multimodal version of explanation. When you say I go to a location, and because of a particular obstacles I end up finding, or particular actions I was only able to take because of the energy I have, or whatever the constraint that you have. So it's really multimodal in terms of the different means of interaction with the environment that I do have. In the context of natural language processing, knowledge representation and reasonings, that's the field where you define and you coin every statement as logical representation. So then when you derive an action, you basically use information which is, or knowledge which is fixed, and then you can reason on that and figure out why do I get a particular conclusions based on the different action which have been used. And uncertainty under AI. So a bit more now on the different on the different machine learning dimensions. So so there are different tools, as I mentioned. If you use well, before going to tools that you can use for debugging black box models, you do have tools which are naturally designed for being debuggable at end. So decision trees is an example. If you have few number of features or parameters, so if I'm a person with an age, with characteristic about eating some particular kind of food, or doing some kind of exercise, then you can build a model which, based on a large amount of data I have, figure out what might be the decision trees that could be built on top of it. So you have decision trees and lists, which are similarly, but just the representation formally is changed. You do have rules, and then you have other language like linear model, generalized linear model. So linear model is it's basically a you take the features which are the characteristic describing your environment or your data. So just get back to the previous example when you do have age and maybe weight or nutrition informations. They are characteristics, and for each characteristic that you put a weight on each of the dimensions. So maybe age, high age or low age is very important, or maybe a kind of food is very important to be healthy or not healthy, or fit or not unfit. So if you put a weight and the model aims at learning and detecting basically a weighted sum of those, and then you have more complex version when you have a generalized linear model, additive model, where you use functions of some of the attributes. So you have a function on top, so it's not only linear. Now you add a bit of complexity here. So it's the additive model. And you have also naive-based models. So there are also the models which work pretty nicely for understanding what the model is doing. Counterfactual, I'll go on that later, and feature importance, partial dependency plot, individual conditional expectations, and sensitivity analysis. So here again, if you need to remember one thing, it's on the left-hand side. You do have models which are what we call white box. So they don't really need complex debugging tools. They just naturally designed for capturing which features are important by getting the weight, and you can easily use those models, and they usually work pretty nicely if the data you have is not so huge. On the right hand side, if you don't have such simple model, then you can use feature importance, partial dependency plot, and other tools which have been available for years. So that's another way for you to debugging the model and get the first insight. So now if we go a bit more on deep neural network, so and that's probably one of the topics usually that interests most of the people, because that's where the black box is. That's where the most of the state of the art in machine learning is for dealing with large amount of data, particularly if we're dealing with text and image and videos. That's where the state of the art techniques is. And usually the technique which are used, it's really based on features representation, really at the pixel level, and you try to, I won't get to details exactly, but here you have the different references, but it's really try to find which pixel might be important for debugging a system. And then you can get rational on that. If you remove those pixels and if you don't get good result, that means that the explanation of those pixels were not relevant, so that's not the right explanation. You do also have prototype version. So prototypes is you have large amount of data and they capture maybe different classes, and usually, well, sometimes having only a pixel-based representation or super pixel or saliency map representation of the explanation is not necessarily all useful for all application and for everybody. Sometimes people prefer to have, give me the top examples or give me the prototype version of this. So if you want to detect a car or a particular bird, you want to get the prototype version. So then if you say that's the picture you predict to be this particular class or this particular kind of bird, then I want to have a prototype version, which is basically, well, an abstract representation of that kind of bird or that kind of cat. And that's only exam-based or prototype-based. And then if you go more in details, if you have architectures with attention mechanisms, attention, they're pretty good in retaining information which is used for doing a predictions based on the previous feature. So it's really this glue between the input and the output, and you have weight that channel the input towards the output. And another one is the surrogate model. So if your model is so complex that you don't really want super pixels, you don't really want examples, you can't or you don't want to analyze attention mechanism. Maybe what you want is something much simpler, and then you can use surrogate model, which is basically take the complex ones, you're feeding any kind of input, you get the output, and you try to build a much simpler model with you define the number of features that you want, and basically you will build the decision tree based on this input output, and the teacher will be your model. It might make mistakes, and your model will do the same mistake, but the goal is to just mimic exactly this particular complex model, but it's something much simpler. So if you look on computer vision dimensions, I mentioned it earlier a bit, but there are very interesting work from MIT in particularly on interpretable units. So that case where now you say you give me the input output, but now I want to go deeper on the neural network. I want to know what is this neuron is really capturing. And you have very interesting work, and some of the code is available. If you check out on interpretable units and dissection work from MIT, they're able to label somehow different neurons or different part of the neural network with labels. So it doesn't need any training. You just need to do a feed forward on the deep neural network, and we basically label neurons based on their activations on previous images. And that's very interesting piece of work that I strongly recommend you to check out. And then you have visual inspections and saliency map, as I mentioned. We have a few examples. So here again, well, as you see, there's plenty of different saliency map based techniques, and we can easily spend 2 hours only focusing on those. Here just a pointer to where you could get more information. So now if we focus much more on an extension of explanation, is rather than explaining, rather than just explaining exactly why the model is getting this explanation. Now you have recent work, and that's recent work that will be presented in May in 2021 at iClear. It's now trying to explain uncertainty. So it's nice to explain when you know you're right, when the model is right. So when you get 80% classification, this is the right object. It's very useful, but actually in many cases you want to know why is the model uncertain. Maybe you want to know this 20%, and maybe this 20% that the model is unsure about the prediction might be telling you more than those 80%. And a very interesting one when they use Bayesian neural network for trying to figure out why we do have uncertainty. So it's going beyond doing a predictions. And basically, here in the context of digits, what he will tell you is say, okay, I think it is 8, but actually I'm unsure because there's for me this part of element is not really 8. So there's a strong uncertainty, and if I will have only considered these dimensions, so if you look at the different 7 or 8 here I have as examples, and it's maybe predicted as a 0, they say I have a strong feeling that this dimension I'm unsure about. And then if you give that to the user, they may say, okay, I definitely agree with that. And sometimes explanation on the uncertainty is much more beneficial for understanding a model. And now if we go a bit more toward more semantic interpretation. So there are really a field now where where we try to dissect or capture the inside of the neural network and try to labeling or capturing information or starting representing neurons. One of the examples is the work from OpenAI. So you may have seen the work that have been done recently on Daily, on Clip, which is one of the new neural network architectures, and based on large amount of data. That's and what they did is they designed a new tool which is called microscope, and it's aimed at fully analyzing the neurons. And basically they use Clip as their own architecture, and they try to see what is this neuron capturing. And by why I really mean visually, what does that mean? So they go inside the neuron. They have very nice libraries called Lucid for coloring or for transforming the neurons in something as a human we can make sense. And here you have example where you see windows, car bodies, and wheels, and that help you capturing the inside of the neural network. And even beyond that, you have tools on compositionality of explanations, where they basically use the work on network dissection from MIT, and they try to see if a neuron, it's not only one label. So initially the work from MIT was trying to label a neurons by one concept. And what here they try to do is to go beyond and try to make composition of concepts. So maybe this neuron is firing when I get two concepts, or maybe a negation and a color, and that goes much beyond what have been done so far. And that's very the latest of the state of the art of what is really done in this field. But again, here it's if you really want to go inside the architectures, and it's not everybody wants, because it needs much more tools. I don't think this is mature enough to show to or to use by stakeholders, because it's very at the fine grained level of the neural network architecture. And we have tools from Google, like ACE or TCAP, that have similar spirits, and I strongly encourage you to look at. So the next sessions, as we have 45 minutes left, as application and lesson learned, and then we move to code. So so next I'll show you a few videos. But one thing I wanted to mention is, and where I think, and some of the experts in the field think that explanation AI is going, is really by fusing and combining the stochastic dimension of machine learning and the semantic representation of labels that you use for capturing objects. So here it's an example where you do have a picture and you do object detection. You can do it in a usual way, or use faster CNN. You do object detections. You use YOLO, and you get you define your threshold, and you detect the different part of the object, and you're done. And what we have tried to do is say, well, maybe it's everything. Well, actually, everything is taken out of context. So it's only the image, whatever the object one. So here you have a paddle and you have water. If it's connected or not, well, the system doesn't really care much. You might see the correlation, but it's not really used as a causation. It's because they are not really, well, they might be connected sometimes, but not every time. So what we try to do is to say, well, paddle and water usually, well, they fit together. And where we get this evidence, and usually you get this evidence when you look at content from Wikipedia and other source of information. And Wikipedia is very source and rich information. It's a very rich source of information when you get information on the different common sense knowledge. So then we say, well, why not using those to see if paddle and water does make sense as co-occurrence, and if they do co-occur a lot in terms like Wikipedia, maybe they should be, maybe when we detect those two objects, maybe they should be boosted up in terms of accuracy. And here what you see here, the both dimensions. So there's a both, and it's not detected in the first place. In the first place, in left image, you do have the paddle, you do have the water, you do have the people, but the boat is not detected because it's it's very crowded with people, and it can figure out there's a boat. Actually, it is, but the threshold is so low that he won't show it. So what we want to do is we want to boost some of the classes to be captured as object detected. And for doing it, we say, okay, let's putting the threshold, let's consider much more objects, but let's do a cross validation with terms that co-occur in Wikipedia or in common sense knowledge. And if do boat and people and padding and water, they do co-occur together, that there might be a chance that they might be the terms that we should see it. And if we see it in the image, if the score is too low, then we can boost it. And the advantage of this technique is you don't need to retrain your model. You take it as it is. The only thing you need to take is all the object detected, all the threshold, and just figure out the co-occurrence that you have in other common sense knowledge. And it might be something you do have in-house in your particular company because it's very niche domain, or it might be common sense knowledge, and then you can start having much better results. And we end up having a much better level of accuracy in this particular context. Okay, so next use case, so I'll move to some videos now. So yeah, I'll do the voiceover. Okay, let's get ready. Because that's the platform we built for building explanations on different use case. And what you do is you load data, so it's working on different use cases. So a financial one, and in context of air industry, image classification for detecting particular object. And what you need to do here in the context, you do have an image and you want to get it classified, and you want the explanations. And here, well, you see the different superpixel used. So that's one case. Another case, you pick not only image, but you can pick tabular related data. And here the goal is to you build different model and use counterfactual. So here I'll pause the video for a second. And what you see is we use 4 different models. So we use K-neighbor classifier, a perceptron classifier, gradient boosting classifier, and what you see is the different features. And in counterfactual explanation, what you have is they give you, I do predict this to be of particular class. So here it's a context of finance. You try to detect if a loan will be accepted or rejected. And what you see in green and red is what you need to get higher or you get lower to get approved. So basically, this is a case where the loan has been rejected, and what you need to, yeah. And here in red is basically what you need to get done. So so for instance, in green, you may need to get a salary up to 35 points, whatever this scale means. And you have other features, and they will tell you if you manage to rebalance your different characteristics. So you have your application, maybe your age, the number of your salary, where you're living, your credit history, and so on. They will tell you, well, so far you rejected, but if you change those, next time you will be granted. And well, as you know, there's a few parameters that you can change. So and you can lock it on the right. So the age is not something you can change right now. So you can lock it, and you can say, now if I just reload it and we'll just redo it again, will I get the similar results? And then you update, and you will see that different constraints change. Some will stay untouched because you constrain the system to keep them untouched. And so in another context, you pick other example of data, and we use Shapley values. So it's another techniques from the game theory which is used. And what you do with your platform, and you can save it for later. I have another application where we use well knowledge graph, which is structured information, so in the context of medical information, where we do have ontology representation of disease and so on, and we want to figure out explanation. Then and here you can see the different expansion which are captured, and then later on, if you use one use case or the use cases, then you can easily analyze the results. Okay, so I'll move to another one. Yeah. So the second video is some work we're doing with a startup which is called Zetam, which is based in Montreal, and that's a very good example where you do analyze the inside of the neural network. So here we do object detections, and as you can see the inside of the neural network, and what is very important is you can see the different activations. So so you can see the different activation maps. So here it's really when you're inside the neural network, you get predictions, and maybe you want to see some of the channel or some of the neurons. Some are dead, so maybe they're not doing the right thing, and you want to see what kind of result you get. And here it's an example where we use GradCam for analyzing the different results, and on the different layers you see the different contributing pixels, and then you do use it for getting the final. And here the explanation is, well, detecting an obstacles, and you say it's the obstacle have been detected both on the at the work level and under the tunnel. So yeah, so that's another context in the context of trains, where they use they considered in a LiDAR environment. So it's operating on the LiDAR environment, and they take different objects, and we push it in here towards the end. And then it's basically we capture it, and based on the explanation, it will stop it because we'll get evidence that it's that's an obstacle. So it just starting stopping, and it would just stop just before end up the obstacle. So that's the second example of application. So that's the same. I'll squeeze this one, and oops, yeah. Yeah, so I'll move to another one because it's much more visually appealing. So okay, so that's a context, that's a work which has been done with Accenture, where we try to detect and explain abnormal expenses. So what you see here is you have the different dimensions of employee expenses. So you have the expense ID, the amount that they spend, how many days they were traveling for, which time of the year, and you have the information about the model predict this to be an anomaly or not an anomaly. Okay, so there's an interface you can change, and you can select the different anomalies, and you can get the explanations. And here the goal is really to figure out if it's the system flag it to be an anomaly because of different dimensions, and the system is trying to challenging the model and saying, okay, you mentioned this is an anomaly, but let's say and compares with depending on the dynamics of the city, comparing to the behavior of the persons. Is it really an anomaly, and what might be the explanation if it is or if it is not? And here what you get is you get different level of explanation, where you do have information about if it might be a fraud or it might be external events, and if it's an external events, you do have the category of events. And here the case is we get high expenses in some cities by some employees, and we try to figure if it's something which is individual caused by the city, and again by high expenses, maybe the accommodation which is unexpectedly high. So and you need to get evidence from the surrounding events in the city, and maybe a large event putting the price of accommodation much higher than expected, and not something you will get easily. So you need to get a tool that diagnose the rationale behind. So you can do it after you get the expense, but you can also do it for doing prediction. So when you do predict, you may want to know what might be the cost, what might be the likelihood of having an abnormal expenses, because the city will be in a particular mode at a particular time. Okay, so that was the next video. So and this one was one you've seen. This part was done with Accenture, and and squeeze this one. So okay, so we are 35 minutes. I think we're good in timing. So I'll pause now for a moment and check if there's any question. Okay. Okay, so I'll pause again for 15-20 seconds, just if you have questions, because now we'll move to the code session. So please, if you do have questions, feel free to post it in here. Okay, so I don't see any yet. Okay, so let's move to the coding session part. So again, the only requirements that is needed is that you need a Google Colab account. So you need a Google, or you simply need a Google account for that. And then you just need to go to the link and make it. I will be working. So you just follow this particular link, and then you will land in here. Okay, so let's start. So I already won all the different cells. So again, some of the work have been reused. So I gave the credits at the very beginning of each of the Google Colabs. Some have been updated or changed or needed to do some refreshing. So here it's one example. So here you have a nice video from the author here. But what we're aiming at doing is aiming at using Lime, which is one of the state-of-the-art tool for doing explanation. So yeah, so you just run the first command. You get the Inception v3, so which is one of the model we will be using here. Then you read the image. So here, this is the image we use, and it's a classification task that we try to do. So there are a few manipulations of the image. You get the class prediction. So again, using Inception v3, you get the different scores as you said it. So with the confidence score, so they mentioned as Labrador Retriever here with 82%. And then you want to get the extension. So here there are a bit more details on how they do it, but it's here I just want to show you how you run it. So and then where it's done, it's computing super pixel. So you can define the number of the kernel size that you want, different informations to restructure this particular superpixel, and what you will try to see if which superpixel might be important for doing the explanation. And then you do random perturbation. So it's basically you putting on and off some of them, some of those superpixels. And here is an example where you do a perturbation here. So basically you only see those elements and you try to see if I run this, do I get the same results? So if I get if I get similar results, well, that means well, similar results means that whatever I put, whatever I masked was not important. But if I do mask something important, which might be here, it will put the completely. It will shift the class completely apart. So then you do it. A bit more explanation. And then at the end of the day, what you get as explanation is you try to capture which of the informations is the most important. So if I do remove those 4 elements, I won't be able to reconstruct the same classification. I will have a huge impact on the results. So that's the final result where you get the predictions. So and you can take your image. It's work on image and text and other data. So feel free to use it. It's you can use it out of the box. Take your picture. See, well, first check that the classes are captured in the class representation, and if they are, then you can debug it and start capturing explanation. So let's move on Lucid now. So that's the OpenAI work I mentioned earlier. So this work on here I mainly use the well the Lucid tutorial, and here we go deeper in the neural network. So we will try to capture the inside of the neural network. So try to have a visual representation of each of the neurons. And again, here, very easy to use. You simply need to use Lucid. There's a few imports that come with for doing some transformations and manipulation. Use Inception v1 as a model, and here you define a particular layer and a particular unit that you want to use. So here it's the mix for A of that's Inception v1. So that's this particular layer, and that's this particular unit. So that's the ReLU 476. And you pick anything you want, and you can get all of those layers here. They are defined in here. So you can check it out and try with any layers. And this is the representation. This is what you will get as a visualization of the neuron. And then you can get a bit deeper. You can so I think this is the 465. That's another neuron, so you can see a different visualization. And also what you can do, you can start combining channels and neurons and try to see what if I do combine those neurons, what they will look like. And again, for human, I think it's probably where it's, when I was mentioning it's less mature for a stakeholder to use, because it's getting more complex here. So how you do interpret, it's basically the anything that match those kind of patterns will activate strongly the neuron. And then you can do different kind of transformations, and that will basically transform, and you can change colors, information, so it will look different. Yeah, and change with different parameterization. Yep. So that's about this one. So now I'll move to the GAN dissection part. So the GAN dissection, it's really try to dissect again the neural network. So we go again inside the inside the neural network. So again, here's the link. You will have access to it. You just need to click and run on cells. We'll use a pre-trained GAN generator here. So we use a particular GAN. So this is the progressive generator here with quite a few number of layers. And then you can start doing and inspecting the internal representation. So you can visualize the network dissection. So again, it's a GAN. So it's aiming at generating new image data distribution that is. So just show you example of what you get first. What is important is when you look at the explanation dimension. And this is the different heat maps that you have on the different neurons. And you see here the different units, and which unit, which part have been strongly activated, which pixel have been strongly active, have been used for firing this particular unit. And then you can collect even more statistics using those particular visualization. But what's more interesting is in here, it's when you so keep in mind that it's a segmentation task here. So if I go down and you try to see what's the label of the unit, because that's the objective. So one thing is way to figure out on this unit, so here the 335, if it's Grace B, and they compute intersection over union. So you see then where is the grass has been captured, so up, down, and up here and over here. So you see most of the time it's right, while here not so much, but but that gives you, and here persons, it's pretty good on this one. So on this particular unit 43, it's capturing on this image the right person here. It sounds like there are some over here. On unit 149, it's capturing roads, and it's well, always on the bottom, so it sounds about 500 different units. On unit 233, on the different pictures, it's a dome. So again, so that gives you a sense that some units, they are pre-defined to capture some particular meaning or labels, and here they're doing by doing feed forwarding and computing intersection over union of image and all the labels that they have, and again, I'm oversimplifying the approach, but it's computing the intersection over union between the class and the descriptions and the different images that they have in here. And you have more example over here. So that's something you could try on the neural networks that they have used. You can use your own ones and use the same approach. So you just change the neural network. You don't need to do a training. You have your model, it's trained in a way, and what you want to do, and if you want to do, it's really to capture a bit more of semantics of the neurons that you have inside, and maybe here it could be used for debugging. So example of if I go, if I take the previous example where you do have road B, and maybe you say, well, this unit 149 have an I over IOU, but there's no road attached, and it's always making a mistake. What if you remove it? At least it won't make a mistake, or maybe you that gives you insight of what you can change. So that's the one I wanted to show on network dissection. And then we have example-based explanation. So here there are a bit more because you need to get some data. So you need to replicate the data which is over here. So you need to get the code, and you need to push the data in a particular location in here. You need to have the data, and the data you can get it from the drive. So here is not as easy as the other one. The other one is just click. Here you need to do 2 steps. You need to collect the data, put it in your drive, and it should work. And what you get here, it's really trying to explain, but by finding some examples. So again, the model is trained. Here we don't do any training. It's only we want to interpret and figure and find the behind. So
Freddie, just a note, we've lost your audio, so it may be a bandwidth issue on somebody's end, but I've lost your audio.
So usually the one before the softmax function, and that's the one that you use for comparing examples, and basically that's in another dimension space, so that's latent space, and that's what you use for comparing examples. So that's this particular layer, and flattened one you see is the one here, 200 dimensions. And so you use this one, and here the goal is to so we have a particular sentence, so that's the review, and they will try to find the similar ones again in the latent space. So here the explanation is again is not at the neuron level. It's not something at the pixel or at the features level. It's figure out examples which are the same in the latent space, and you can compare to yourself, and you can try different example, and you will see, well, that could give you insight of, well, those examples are quite similar, so that sounds good, or they are not. That means that maybe the data that you use for doing inference on is not maybe relevant, so maybe you need to build your own model. because here when looking at the different, it's also depending on the case. So if you do positive or negative sentiment analysis, for instance, and if you see that the data that you have as comparisons are very far, you might question the model, the data used for the model, maybe the architectures, and that's a tool for debugging. So that's something useful. Okay, and the second one on image. So an image, so again, same configuration as before. You need to do a few installs. You need to get the data. The data is available on this drive. You need to do some setup. Here we define the number of classes, and we do have the model already built. So again, it's machine learning based. So model are built. So we want to see if we get the right explanation. So that's the architecture that we use. Here again, it's example based. So we will need to do a comparison at flattened one. You can do it at different ones. You will get different results, but that's a good one to start with. And here you have the example. So and you'll see good ones and bad ones. So here we predict this to be a truck, this to be a bird, an automobile, and a frog, and again a frog. And you can see that which of the similar examples that you get. So for birds, they're quite similar for automobile also. So that give you information that okay, this has been classified, and maybe actually, well, I think the more I see this, and the more I think it's not so useful for giving you an explanation of why this is a track, but at least that give you that the model I have some similar examples. So when I show this, you get a good classification and because they are similar. So if you get a wrong classification here, well, and you have very different examples, that means somehow your data is shifting and is from the test, and it's not, you don't have a representative data in your model for doing a good job. So usually good for debugging and saying, okay, I'm simply using it, get similar example in the latent space, they're quite different, I get not good classification results, then you can start questioning the data that you have in your model. And it's really useful for this. Okay, now we go to ECG. So I'll show on text, I'll show on images, and now I can show that it's also working on ECG data. So like cardiogram data. So again, same procedure as before. The only thing we change is the model, because the model is trained on different data. It's the classes. So we wanted to classes different level of different kind of bits. And the architectures, that's the architecture we used, and similar process. And here what you get, let me go down. Yeah, so you get these results, fusion bits, and again you see similar results. So you can see well, similar patterns. And again, this could be useful, again, not really for explaining why this is a fusion bit, but what are the closest examples in the latent space. And again, if you get not good results, if the accuracy is not good, it's very useful because he won't be able to figure out the closest one, so he won't be able to do a good job in doing classification. So that's very useful for debugging your work. I'll move to the next one on, I think I have another one before. Yeah, on graph. So you might use graph data, so which is structured information. And in this case, you might question, well, okay, you show it, you can use it on text, on structured data, on image, on ECGs, on kind of well, plot-based diagram. But can we use it on graph? And I think it's a good question. And the more and more data and structured information is available, then can we use those techniques out of the shelf? So actually, I've been trying this, and I've been using some work and from Captain. I've been using some work from the first leak here that you see here, and Captain is the Facebook API for doing explainable AI. So here you see all the different techniques that they use. They use SHAP and Gradient SHAP, DeepTIFT, and many others. And that's probably a very good library to start with, just to get different explanation. You put the data, you get different explanations, and that is being tried on Graph. So that's what I wanted to show. And again, that's a pretty good notebook I find available. The credits are over here, so you can see the initial version on the very top. And there's not much that you do. So so it's a multi-genicity. So you basically try to detect if a particular molecule will be might mutate over time, or it's subject to mutate depending on the molecules that they have. So that's the goal. So well, there are a few setups that you need to do. You have the visualization of the molecule, and that's captured as a graph. You use a GCN for capturing the graph representation, and so you do train your model because that's a classic classification task you need to do. So there's nothing really novel here. So we need to do a bit of training, and then you apply the Kapton attribution. And Kapton, what he will do is when you build your neural network, then it can start, and IG here is for the integrated gradient, and you can use others, so you can use Salency and others, and they will tell you and will show you the different importance. So here again, it's the initial version that you have, and right here it's the integrated gradient and the Salency, and you see that you have a very strong weight on this double ONC and the double ONC on the right, but for both, and you see that they are where the weight is much larger. So that's where you can and actually it's known that those are subject to mutate, to make molecules subject to mutation. So that's very good exercise over here. And again, it's based on a model which is built, and you try to define which of those particular elements might be responsible for a particular classification results. And because it's a multi-agency classification task, that's the property that those particular part of the molecules will have. Okay, so I have 12 more minutes to go, and I'm nearly done. So sorry, I'm going pretty quickly on the code, but you can easily replicate it and go in more details. And I'm open to any question that you have. You can send me a note, or please feel free to ask me questions in the live chat. I can answer. So yeah, and final slide on the code part is on the different evaluation. So okay, so it's all right. I think I can go towards the end because that's at the end of that you get the result here. So that's where we basically use the same data as we've seen before, but we either use example based or integral gradient based, and I think that's a code that you can easily reuse and say that's the data I have. What if I do apply line? You do apply line, and on this is what you will get. So you see this is classified as cat because of this reason, but it's not a cat, obviously. But you can see the different well, challenge that you have, and it's not a cat, and then and here it's a frog. Then you have the anchor explanation. Well, same, you do apply and say, okay, this is a truck because of this particular part here. This is an automobile, and this is a cat because of the thing on the below. So okay, that sounds. And you can see where it's getting confused, and you get a sense why. And you can use SHAP where I show the explanation, the super pixel here, which might be responsible. You can use the Salency map, the GradCam++. It's another version of figure out the explanation, and examples. And I think the good example here is this is not a cat. It doesn't look like it's something like a reindeer, And here, if you find these examples to be the closest one, that means your data doesn't really capture many reindeers, and maybe that's simply the reason why. And so that can give you good example, good reason why. All right. Okay, so I'm done with the code part. So I'll move to a bit more tools for you to use. So it's much more now a toolbox. So again, slides are available at the end of the slide. I have the links where you can download them. But here is the different tutorials, workshop, conferences, challenges that you can check out if you're interested in the topic. Here are the different resources. So I mentioned Captain ones, which basically replicate work from Shapley values, from integrand gradient, and many others. I mentioned Lucid and Lime. You do have all in here. I mentioned Google TCAF. I mentioned the MIT dissection work. I mentioned the OpenAI Lucid and the microscope. So they're all over here. So feel free to check it out. So yeah, and just to quickly wrap up and give a bit time of questions. So XAI is a very hot topic. There are very interesting work done in the US, which is done by the DARPA. In Canada, it's some work under the DEAL project, which aim at building robust machine learning systems. In Europe, similar initiative in the AI for EU, and more recently on robustness with the Confiance AI in France. So there are a few projects that try to address those challenges and much more towards how you make machine learning applicable in critical systems. And conclusion, so so what we aim at doing is really making machine learning system much more interpretable, reveal and protect new vulnerabilities, protect subpopulations, understanding why a model is bugging, and how we can debug it, how we can implement the right explanation. So align algorithm with human values. So that's something you can tweak algorithm and maybe the data or the data collection part, and how you preserve human autonomy, and very importantly, how you scale and industrialize AI. And so explainable AI is motivated by real-world application in AI. It needs of actionable XAI. So I mentioned this at the beginning, but it's very important that if you want your AI to be applied in critical systems, whatever explanation that you get, you need to action on it. It's not something that say, okay, that's a certificate, and you just say, okay, I have it. It's something that you can use for improving your model, for debugging it, for debiasing it, making it more fair, or whatever make the model much more safe and trustable to be deployed in critical systems. And it's not a new problem. It's a reformulation of past research challenges. It's multidisciplinary, as I mentioned earlier. It's very interesting. It's very hot. The more and more tools, libraries, and research work done in the field, and you see much more application and much more and more deployed. So it's really now in the industrial settings. And as I'm working in Thales, we do need those tools. We do use those tools, and our stakeholders, they do cry, particularly when we deploy in planes, in trains. They need that trust, and they need those models to be robust. And to get them robust, they need to get understanding on why they do operate this way and what needs to be changed during data collections, annotations. It's something that we need, and my stakeholders needs. And many other open questions, so I'll list them here. I won't mention them, but there are interesting future challenges, evaluations. It's crucial, and so I wanted to sub 5 minutes before the end, so we have time for questions if you do have questions, guys. And again, whatever I share, it's most of it is accessible open source. I gave links here or there. I collected the content, so feel free to ask me any question that you have. Slides are available at in this particular link, and if you have questions, feel free to send me a note. I'll be more than happy to answer any question that you have. and we have a 4-hour sessions if you want more details on these 90-minute sessions. Please go to the YouTube channel here. There is much more you can find out. So open to question now, and that's close my talk for today. Okay, so I'll pause. I just change screen because I don't know if the question or come to my chat here.
Yeah, there's no questions yet, but
Okay.
they may have come to you.
No, I don't see any question. No question. No. Okay, so I'll pause for the 4 minutes, and if you want to interact or comment, or please let me know. I'm more than happy to share anything that you might need. So yeah. I'm on the chat now, so if you do have questions, please shoot.
So there's a question that came in the application chat, which I'll try and read to you. It says here, does having XAI solve the issue of deep learning models being a black box? Traditionally, some companies use simpler models for explainability. So does this make deep learning viable for this use case?
Well, it's a good question. So, the end goal of explainable AI is to try to demystify, well, neural network for the end user, so they can make it usable. And well, I think most of the people, they want to use it because they're impressed by the performance that they have. It could be in terms of accuracy or whatever metric that you have, and they want to get explanations. But sometimes they do already have existing much simpler models, and I think well, there's probably two sides of it. So well, first, I would encourage to start with simpler models because they are easier to debug, they are easier to explain, and they're easier to change and updates if you want. So I would really start with that. So if that's working for you, shifting for a deep neural network, it might be tricky in the short term, and you might not get the explanation benefits afterwards. And that's the reason why people studying more and more explanation in deep neural network. It's because now some people already move in there and they want the explanation, but it's much more complex. So I would say if you really want explanation and want to easily be flexible and change and adapt and refresh and understand, well, stay in the simplest mode version. If the accuracy is not there and you need to because that's what you want and what you're aiming, then move to the deep neural net dimensions. But in terms of interpretation, it's more complex. Again, I mentioned tools. We show tools, but is it something that you will be convinced with? Is it something that your stakeholders will rely on? That's probably the next question. So to be honest, I will step back and say, okay, who do I serve and what do I need to get with this model? And then if it's explanation is a must, go as simple as possible. And explainable AI the field is mainly aiming at demystifying the neural network and getting explanation. And that's probably where you need to go if that's if you want, and you have huge amount of data in text, images, or huge amount of graph. But if you have small amount of data, I won't encourage just to move to deep neural nets for the sake of doing complex XAI in the field, because it's very rocky and it's maybe plenty of painful my experience that you may get. So that would be my advice.